I'm not even sure which dimension is easy to do it. I think it's even dimension, so it's easy to do it. Okay? But regardless, the long distance behavior always looks like this.
Basically, you're integrating all this K to KD and the one.
That's right.
Yeah. Then the contribution for which it is highest, you're keeping.
So there's a power in front of this,
No, but you have not.
which has to do with the integral.
You have not integrated the other case, right? You only
He has
given
integrated, I think, right?
So that's the method of steepest descent, is to integrate the other case. Because this integral I can do exactly.
Yeah.
The other ones I cannot, unless I'm in some special dimension, right? But even regardless of what it is, just look at that integral, okay, and ask what can it possibly do, right? As x increases, this thing forces, the only significant contribution really comes from small values of k, okay? And so therefore, I just do some integral over small values of k and I get something. Okay? I don't care what. But that something is going to be a power law contribution. It's not going to be an exponential contribution. The exponential contribution is going to be this.
So
Okay.
sir, it is saying to replace the same integrand by its maximum value.
That's right. That's steepest descent, right? For a real integral, that's what it is. It's a complex integral is more complicated. Right? It's just a real. Okay? Good. So this tells you what the correlation length is. So now we know that the correlation length is 1 over m. So it's basically 1 over square root of p minus 2.
Sorry, I have a question.
Yeah.
In the momentum space, when you have written the coordinator between phi k and phi k prime,
Yeah.
there you should use retarded propagator or just because
No. I don't think quantum mechanically. No.
because
There's no
otherwise
quantum
you cannot
mechanics
do the
There's no quantum mechanics here. No retardation, there's no time. I don't have any poles on the real axis. I don't need to worry about retardation or. This is like Euclidean quantum field theory. There's nothing, there's no time.
because you have
Nothing
to-
retarded. Okay? Everything is well defined. Except maybe at the critical point. That's the only place where singularity is defined. And remember, I'm not going to be worried about ultraviolet infinities. I don't care about ultraviolet infinities. I only care about infrared infinities. Yeah.
after this steepest descent method. So how can we get this e to the power minus xa that is from this?
So let's look at what the steepest descent does, right? What does the steepest descent do? It says, you give me some integral, let's take a one-dimensional case, right? You give me some integral and it looks like e to the power minus f of x, let us say. Okay? Then you say that I'm going to minimize this function.
Yes.
I'm going to look at the point where it's a minimum. Okay? Near that point, what is going to happen? So let's say that point is some x0. So f prime of x0 is equal to 0, right? The function is a minimum. Very good. So near x0, what will the function look like? It will look like some f of x0, the value of the minimum,
Yes.
right? It's a minimum. It has to be a minimum, right? It can't be a maximum or some other kind of extreme. It has to be a minimum. Okay, good. So you do that, and then you say it's 1/2. The first derivative is 0. So it's f double prime of x0 times x minus x0 squared plus other stuff.
Okay.
Then you have some Gaussian integral left of fluctuations. Standard steepest descent, right?
But you need the maximum because the e to the power minus.
You need this to be a
Minimum.
Minimum.
The integral will be maximum.
Because e to the
you
power
need it
minus.
to be a minimum because you want this guy to be bigger than 0. Otherwise the integral will diverge. You don't want that. Okay? Sometimes if the only thing you can find is a maximum, you can distort the contour and go along the imaginary direction to get something. Okay? You've seen this, right? In your mathematical
Yes,
class.
now I can just read it. So now that is the first part of the integral. the other integral over other k's are intact outside.
Zero dropped.
So okay, so instead of talking, I should have just done it, right? This is always my mistake, I like to talk. So, okay, so what I'm saying is the following. So you have your d to the d minus 1 k perpendicular over 2 pi to the d minus 1, right? And then you have this function of k perpendicular squared, correct?
Yes.
Supposing I take the denominator as well and put it up there. Okay, it's only a function of the magnitude of k perpendicular. So I do the spherical integral over the d minus 1 angles. I get something. Okay, then I get a single one-dimensional integral, which is of that type.
Okay.
Okay? So go home and do it. Okay, it's worth doing. Alright, and the result you get is this up to some powers. The fluctuation integral will give you some powers. Powers of x. Okay?
Okay, yes, here that I thought that the first term will reduce to this term and the rest of the integral is the d minus 1 spherical integral.
This is that integration.
Okay.
Okay? And this integration is going to give you some factor, some angular integration. Okay? So sd minus 2 times the magnitude of k per to the power d minus 2, okay, d to the minus f, k per, something like this. Then when you do steepest descent, you put everything up into the exponent, and then you minimize it. Okay? Good? Alright. So you actually, do you believe me? This is an important result to believe, and then to go home and actually verify. Okay? Because this gives you a critical exponent from mean field theory. Because this says that the correlation length is 1 over n. So remember, I defined it as e to the minus magnitude of x divided by the correlation length. So how does that correlation length diverge as you approach the transition? M squared was r, that was t minus tc. So this is the square root of t minus tc. Okay? Good? Alright. Now, let's extract one more thing from here. Since we have this integral, I want to extract the anomalous dimension of the field. Okay, so remember, the definition was the following. If I set at e equal to tc, then at lossless spaces, this should go like 1 over the magnitude of x to the power of d minus 2 plus eta. That defines the anomalous dimension of the field eta. That's another critical exponent. Okay? So we sit at the critical point. So what does the critical point mean? It means m squared is 0. Okay? T is equal to t. So you sit there and then you say that this guy is basically d to the dk with some powers of 2 pi, which are not really important, d to the I k dot x over k squared. Alright? In any dimension greater than 2, this problem is completely regular. This integral is regular. So let's stick to dimension greater than 2. Okay? So here, what I can do now is I can scale instead of by m, I can scale by x. Okay? So let me define a new variable, which I'll call k prime, not k. Let me call it y. Okay? Y is k times x. These are both the magnitudes. Okay? Again, of course, this doesn't depend on angle, right? All right. So now we just count the powers and ask what happens. Right? So what is this now? So I have d to the dk. So this will give me d to the dy 1 over x to the d, right? That's d to the dk here. There's a k squared, so I get that. Okay? And there's some 2 pi's, which we don't care about. Then e to the I, let us say k1. Okay, it doesn't matter which k it is, it doesn't matter which direction it is, right? And this is actually y1. Okay? And then this is y squared. Now this integral is completely independent of x, just a number. So therefore, the power should be 1 over x to the d minus 2. That tells you that the critical exponent eta in mean field theory is 0. Okay? Good?
It's in also exponential, but how do you get this 1 by x?
Very good. So that was for t bigger than tc. It had a finite correlation length, and everything decayed with the correlation length. If you sit at the critical point, the correlation length diverges. It's now infinite, because the problem has become scaling there.
And you will be seeing
Is zero.
in kinesis.
M is 0, correct.
And then it is one dust.
Right. I could only do this when M was not 0, because otherwise there will be a point where the two poles come and pinch the real axis, and then I'll have to do something else. Okay? Yeah.
You told that in mean field theory that it is 0. But here we are completely considering that grad phi term. That is giving me k square. Then that term is not in mean field theory. So,
So this is, when I say mean field theory, I mean now a generalized version. I mean the Poisson effective action, because I'm including that in mean field. Okay? Maybe the correct terminology is to say Ginzburg-Landau. Ginzburg-Landau theory, he does.
You have also considered fluctuation.
Yeah. But only in a very limited sense. I haven't really taken them seriously.
And you have considered lambda to be 0.
I've considered lambda to be
If
zero.
not lambda
That's
equal to
correct.
0, there will be.
That's right. Okay? Good? Alright, so there's one more critical exponent, and that's alpha. So let's compute that. We could have done that without all this correlation function business. But let's go back and do it. It's very quick. So, remember what alpha was? It was the specific heat, the singularity of the specific heat. So, in mean field theory, if T is bigger than Tc, then the average value of phi is 0, and then the free energy is 0.